All right, we're looking at electric fields and field strength today. So, electric fields. I'm going to start out with what is a field, anyways, right? It's kind of a weird word. So, field theory intro here. The four fundamental forces in nature. You may have heard about them already, but I'm going to run through some things here. From strongest to weakest is the strong nuclear force, the electromagnetic force, and then the weak nuclear, and then gravity. And they're all like what we call non-contact forces. And so that's what we're talking about is like, how does a force exert without contact, right? So they exert over distances, very large distances, in some like gravity. And so that's referred to as action at a distance. So how does that happen, right? So field theory was first developed to help scientists visualize, understand the idea of like how this works, right? So eventually scientists realized the field itself, they sort of thought there was a medium, right? But then they realized that the field itself is basically what we could think of as the medium that the force is acting through. Um, and so, yeah, field theory explains force interactions between objects in terms of fields. So a field of force, right? A force field, if you will, exists in a region of space when an appropriate object placed at any point in the field experiences a force. So that means like a gravitational field around a mass. You know, you have around Earth, there's a very strong gravitational field. So if you put a mass in a region around Earth, it'll experience a gravitational force because it's in a so-called gravitational field. What we're going to be looking at here would be electric fields. So you have an electric charge put near another electric charge. It's going to experience an electric force. So there's an electric field, right? So that's the idea. Obviously, when I said force field there, kind of invokes the idea of like science fiction, you know, using the idea of force fields and so on. They have these like protective force fields and so on. The so the Obviously it's not quite science fiction like that, but force fields actually do protect Earth, even actually, right? The electromagnetic field around the Earth protects the Earth from cosmic radiation from the sun. So this picture here shows it kind of better, more realistically, right? So you have this cosmic radiation coming along, and it gets deflected because of the magnetic fields around the Earth. So yeah, so let's start out with the familiar gravitational field. You'll soon see that it's kind of strange, actually, that it's actually the least understood. I've already talked to you guys about it, actually, about how I don't many think that gravity is not a real force. I think I did a lesson previously about that, either in grade 11 or grade 12. I think I did it for you guys too. Anyways, so look at you have a mass, right? Well, what direction is the gravitational force? It's towards the center all the time here, right? So you can place a bunch of arrows one by one, or I just have it ready to go here, right? So the existence of a gravitational field is shown by those forces. What is that gravitational field? If you go on further in this, Einstein essentially proposed the idea that gravitational field is actually a distortion of space-time. And so the mass of the Earth causes space-time to warp, and same with the moon, and everything's traveling on geodesics, or straight lines in curved space, they call it. So if you think of walking in a straight line on Earth, you're not actually walking a straight line, because if you walked forever, you'd walk all the way around, right, in a circle. So that straight line on the curved surface is called a geodesic. So that's what objects do in space-time. They move through straight lines in space-time. But if space-time's curved, then technically they're traveling in a curve relative to other things, right? So now moving to electric fields, we have a very similar situation where we have attractions, right? So we have the electric field shown by the force it exerts, and the weird part, or the new part, I guess, in this situation would be if we have a repulsion situation, right? Like we've already sort of mentioned. So electric and magnetic fields, electromagnetic fields. I'm throwing out that term now. Electromagnetic field I'm just mentioning that now so that you can know that electric fields and magnetic fields come as a pair. Their surround charges when there's a fluctuation say you move a charge back and forth, or a charge gets bigger or smaller. that's considered a change or a fluctuation, right? So that sends out a fluctuation in the so-called electromagnetic field, and that is an electromagnetic wave. So the speed of that wave is 3.0 times 10 to the 8, which you might be familiar with is the speed of light. And that's what light is. It's just a wave traveling in the electromagnetic field. And of course, there's all sorts of different versions of it: visible light and infrared light and ultraviolet light and radar and so on. They're all just waves in an electromagnetic field, even though they seem quite different. Visible light versus not visible light and so on, right? So that's just another visual of the fact that the two are at 90 degrees to one another. Okay, so you have the electric field visualized or shown here as being up and down. Magnetic field then would be perpendicular to that, so it'd be side to side, right? So the electric field shown well, that almost looks like horizontally in that drawing instead, but yeah, those are flipped, I guess, by accident. I was probably just going with what the other page had, but again, we're at 90 degrees to one another. All right. So this occurs with mass as well, with gravitational fields, producing gravity waves. And a while back, I had written here that in a lesson, doing this lesson a while ago, that gravity waves should exist and that they're looking for them and they haven't been observed so far and so on. And suggested, that'd be a good field of research to work towards a PhD, and people have done it. I don't think it was one of my students, but it could have been, though, right? Like it's something that was eventually, thought should exist, and then eventually discovered. So that was discovered in 2015 or so, 2015, 2016. They actually observed the first gravity or gravitational waves. So look up the LIGO, LIGO detector for how that worked. It's pretty cool. All right, so forces acting at a distance because of fields, right? So this is classical field theory we're talking about, and we'll continue to talk about in this course. And then I am going to mention the newer, better, real version. So classical field theory, really good math. You have this field theory equation of GMM over R squared. It's the very similar KQQ over R squared to do with the electric field. These are really good at predicting observations and so on. They're not really explanations, right? They're not explanations of what's actually happening. They're just good at helping you calculate what values you're going to have. So here we go with the actual explanation of things. Okay, so this is not something we're going to do a ton of in this class, but I just want you to know the other version of things here. So if we start out with the one we are looking at, electromagnetism, well, the forces are actually caused by the exchange of particles, virtual particles, they call them. So electromagnetism, there's an exchange of virtual photons between things, and that's if you have two charges that are repelling each other, you want to picture virtual photons being exchanged between the two. So that is what I went one too far there, I think. Yeah, went one too far there. So, no, never mind. I'm on it. Sorry, this is quantum electrodynamics, right? So that's the quantum theory of exchange particles going back and forth between charged particles, and that's what transmits the electromagnetic force. Okay, so that was in 1947. They got that under control, and then building on that, they said, okay, well, there's this force that holds the particles in the nucleus together, the charged particles, the protons, right? How do they not repel apart? Well, they're held by the electromagnetic force. They should be repelled apart, right? Well, they're held together by an even stronger force called the strong nuclear force. And so physicists are kind of not super creative, I guess, on the wording. I kind of like it, though. I moved that around. I shouldn't have. Gluons. So gluons are the exchange particle, the name for the exchange particle that holds the protons together in the nucleus. So these are your exchange particles for the strong nuclear force. And so that, again, 100% confirmed. It's solid framework of math that explains things beautifully. This was put together called quantum chromodynamics, and that was a little later, right? So 68 to 72. 1979 was sort of finalized at this conference at some point. So in electrodynamics, quantum electrodynamics, you need two versions, plus and minus. For the strong nuclear force, they found they needed more variables, if you will, or more quantities, not just plus minus. And so chromodynamics, you might recognize, is to do with color. And so they needed three. So they went with red, green, and blue. And it's actually really beautiful the way it works out, where they have color conservation, and the idea of red and green making yellow and so on all fits beautifully with the model for strong nuclear force. Is just bizarre. And then after that, they got the weak nuclear force. Is even harder to figure out, right? So they're called the W and Z bosons. Again, lovely confirmation of this stuff. All works great. In fact, they've gone even farther, and they've managed to combine those two into a partially unified framework, if you will, an equation that describes both the electromagnetic and the weak nuclear force. Weak nuclear force, you would have hopefully seen earlier in grade 11, to do with radioactivity of nuclei, right? The spontaneous decay of a neutron is your beta decay and all that stuff. That's your weak nuclear force stuff. So that going all the way out to 1983, that was kind of finalized, right? And then the last one, the missing piece of the puzzle, and I mentioned earlier that we think of gravity as being so familiar, so we use it as a model to help ourselves understand things. But if you're thinking about there's an exchange particle for gravity, theoretically they've named it. They call it the graviton. People have looked for it. They haven't found it. We're not sure if it exists. Physicists aren't sure if it exists. So you can spend time trying to find the graviton, and you might get a PhD, or you might just be frustrated forever, and maybe it doesn't even exist. So it doesn't seem like at this point gravity actually has an exchange particle framework about it, and that could very well be because it's not actually exchange particles. It's really just a frame of reference thing, like I mentioned before. So if you're in circular motion, it feels like you have this centrifugal force, right? While when you're near a mass, it seems like you have a gravitational force. So anyways, that's your intro to the idea of the actual, what is thought of in physics theory as what's really going on. All of the stuff we're going to talk about is classical, in this unit is all classical physics. So the idea of this classical interpretation of electromagnetic waves. So I guess sort of. All right, moving on to, so just to recap, because we're going back to fields, right? Away from those exchange particle reality things that eventually you'll learn about. So back to fields, right? So I just explain this weird, and explaining quotes, it's not really explaining anything, right? They just say, oh, well, there's a field, that's how there's a force. And so the familiar field, like I said, even though it's technically not as well understood, when there's a mass, when a mass is in the presence of another mass, mass's gravitational field, I should say, there is a gravitational force on it. And now for electromagnetic or the electric field stuff, when a charge is in the presence of another charge's electromagnetic field, there is an electric force, an electromagnetic force on it. You can see the parallel structure here, right? And that's what we're going to use to help ourselves understand this. So we're saying an electric field, we have this dimension, this region around where there's charges or there's forces on charges, right? It's actually a three-dimensional space. Just be aware of that, of course. We're often going to just draw things two-dimensionally because it's very easy on a page to draw that way. But really the forces would be transmitting in all directions, right? Three-dimensionally. So what is this field idea? We're going to start to try to work towards that feeling like we understand that anyways, by looking at electric field lines. So electric field lines are lines that show the direction and the amount of force that would be on a so-called positive test charge. And this is where that silly definition of current being the flow of positive charges came from. So if you put a positive test charge, it would push out this way. If you put a positive test charge here where my mouse is wiggling, it would go out that way, and so on. So these are your electric field lines, or lines of electric lines of force, they call it. And so, yeah, if you put a negative test charge in there, it would go in, and so on. Make sure I don't gloss over anything here. I think that's all regular. Oh, the other part I want to point out, the test charge is supposed to be, small enough that it doesn't affect the actual overall charge here, right? So you put that little test charge in there, and that's not changing the electric field in the area. It's a minuscule little charge just to see what direction things would be going. So yeah, the electric field's a three-dimensional phenomenon, but we're going to draw it two-dimensionally. The electric field lines represent net electric force per unit charge, right? So this is the net force. If you're at that spot, that's the net force you'd have per unit charge, per coulomb. So, or 1.602 coulomb, I guess, right? Unit charge. So you can't have, right? It's impossible to have two electric field lines crossing one another, because that would mean you'd have two net forces in that area. So it just logically doesn't make sense. You can't have two net forces. So electric field lines never cross just because of their definition, right? You will sometimes have situations where two electric fields are overlapping, if you will. And so they're going to combine to give an overall net electric field net area. And so you'd use vector addition for the result. And we're going to be doing that. So one thing to note, kind of weird about this, generally you're going to see, kind of out of order here, I guess, you're going to see things like this soon here, that you have a large charge versus a small charge, okay? And most people will say like the field line density, gives the representation of the field strength. However, when you have more than one charge, in the way they're overlapping and so on, it actually becomes not as obvious. The field lines don't give the field strength in that case. So when charges are unequal, when you have multiple charges and are unequal, the line density is not an accurate representation of field strength. So if you look at this picture, I've highlighted 16 field lines. So I have 4 of them going to this charge because it's 1/4 of the charge, right? And then the rest are going off, right? So 16 lines come out from this one, only 4 come out for this one. And so that's how they'd pair up. It's not as obvious in the diagram the way it was because there's so many lines. It's kind of hard to tell. There's more lines from the bigger charge than the smaller charge, right? So it's I would prefer to see the diagrams like that, but I mean they show a whole bunch of lines all the time, right? So what this diagram shows is a representation of the strength by having some shading in there as well. So the red areas are where it's the strongest electric field, and you can see the way the electric fields combine at all these different spots is pretty complicated, pretty detailed, right? Yeah. So this is a kind of a neat thing about this. We have, in this case, we have the +4 and a -1. Okay, we're going to have a +4 and a -1 in this area. Okay, if you look at the net effect of that, it's going to look the same as a 3, a quantity of 3. And so I'll show you that here. We've got a charge of 3, +3, in this little simulation. So it looks like this when you're playing around with it, right here. This one here. So you put a charge in place, right? You see the electric field, and then you put another charge in place, and you see the field gets a little brighter. And another charge in place, field gets even brighter. Okay, that's what I've done with this. And so here's 3, and so pay attention to the brightness right here where my mouse is wiggling. And when I go to 4, hopefully you see it's getting a little brighter. So it's like just a little bit brighter. We go from 3 to 4. It's like the optometrist. Which one's brighter, 3 or 4? 3 or 4. And anyway, so 4 is a little brighter, right? If you go now to the 4 plus a -1, right? That should be a total of 3. Now, if I go between 3 and 4 - 1, right, you're going to see the brightness not change. It's delayed here, but the brightness isn't changing. So I wasn't sure if you'd be able to see that super well, and so I put it on. You can put a sensor in place, and this is measuring how much force there would be on a unit charge. Okay, so that size right there indicates the strength. You can see here that a 4 is longer, and then you go back to the 4 plus the -1 for a total of 3. Now it can bump between 3 and 4 plus -1, and you can see they're extremely similar to one another, right? So the further out you go from that, the more it looks like the overall combination of 3. And I'll show you that here. So this is 3, if I remember right. Yeah, there's my 3, right? And then let's say, okay, 3. If I put 3 there, like the sensor there, and then I were to add an extra one, so that's now 4, and then I put the 1 in place, you can see it's like not the same as just 3 because it's close, right? But the further away you are, then the more zoomed out you are, if you will, the more it's going to look like a combined total, which I think makes sense. Another little simulation. I've got a bunch of little simulations to help you sort of visualize this stuff. So let's go to this one here. This one you can change the sizes of them. So I'm pumping up the red charge, right? So the red charge gets stronger, or the opposing negative charge gets stronger, and you can start to see what things would look like here. So this one, oh, okay, this is good. So I can make this one be a strong negative, and this one be a strong positive. So this is what attraction between fields looks like. And notice the field lines are starting in one and attracting and terminating in the other one. So it's like they're tied together. If you make them both the same charge, this is what repulsion looks like. You have these fields that are coming out, and you picture like there's a net force this way, and here there's a net force that way. Eventually they're going to kind of combine where there's going to be a net force sideways. And so it's this net force kind of coming head to head and almost repelling each other, right? Making it actually repel if you think of the field theory of this. In actuality, of course, you've got exchange particles bouncing off them, causing repulsion. So yeah, visualize all this stuff. But and so here's that. This is 4, and then this is a 3, and then this is a 4 and a -1. So again, you can tell here this field pattern is extremely similar to this field pattern, right? Again, same idea. Okay, so large fields, small fields. When we have repelling, you saw that in the simulation. When you have attracting, repelling small charges, less net forces that are, you have a force this way and a force that way, and eventually a combined force of kind of that way, and so on, right? And then the attractions, and so on. Hopefully, this all kind of somewhat makes sense to you. So large versus small charges. You can see this one is trying to push this way, but it's getting like pulled back into this one because this one's so strong, right? Things like that. This one here, this really strong one here is, bending these ones backwards because it's so strong. So you can really kind of see and feel the repulsion, if you will. Okay, so it's just nice to be able to visualize all these things. So I encourage you to play around with the simulations, because it's a luxury that you have at your disposal here for that. So you can change the size of this force. You can add in other forces. I'll come back to that in a second. Other charges, I should say, other charges. So that's this right here. If you want to show what this looks like with complicated patterns of a whole bunch of charges, you can just put a bunch in place, right? So that's this simulation here. This one doesn't work anymore. It was a Java, whatever, it doesn't work anymore. But then I just found this one this morning. It's pretty similar. So I'm going to go to it, and all you have to do is, you're struggling here. Come on. This one here. This one? Yeah, this one. Go to multiple random, right? And so you can just put various sizes wherever you want and see all the kind of different charges. So if I put all the positives together, that's going to combine to be a really strong positive charge. And if I put the negatives nearby, I can think they're actually kind of big enough. go to small negatives here, and you could end up seeing the overall effect. Especially if I bump all these guys up to positive, the overall on a large scale, it's becoming the same as if there's just a positive charge there, right? So normal or same kind of result as before, right? So the more positives you have, the more overall it's going to look like a positive, and so on. Anyways, so I have my old man bracket statement here, right? This type of visual aid did not exist when I was your age. So yeah, enjoy it. Like it's pretty cool to be able to see that at live like that. Okay, so moving on here. The next part is about electric field between oppositely charged plates, so plates with opposite charges. Has a bit of an interesting result or surprising result. So this is just when you have charge built up on them. There's no battery connected, and that's a distinction we'll have to focus on soon when we get to the other version of this. Like when you have a battery connected, it's a different situation. This is just you have an excess of positives here, so you're missing a bunch of negatives. Here you have a bunch of extra negatives. Okay, so you've got a charged parallel plates. And it turns out that anywhere in here, it's always the exact same field strength, which is just kind of a weird thing. So it doesn't matter where this positive test charge is. It can be close to here, close to there, or in the middle, or over here, and it's always that same electric field strength, which is just kind of a weird thing. Okay, so the electric field between parallel plates is uniform. And the magnetic field between the plates is proportional to the amount of charge on the plates only. It does not depend on the spacing. Okay, does not depend on the distance between the plates. I think it probably says that in one of my other spaces here, but I just want to emphasize. Whereas when you look at later on, when you have a voltage applied across, it does depend on the distance between the plates. So it seems like a very contradictory thing because these seem like very similar situations, but they're not the same. If you have just charge built up versus if you have a voltage applied across, it's a different scenario. Okay, so watch for that later on. So aside from some bulging at the ends, there's zero electric field outside of the plates, which is kind of a neat thing. And again, this is the varying the distance between the plates does not change the electric field strength, which is strange. You can't have them too far apart, of course. Like infinitely far apart, you wouldn't have any effect at all. But as long as the area between the plates or the distance between the plates, the area between the plates needs to be large in comparison to the distance between the plates. In which case, you could double the distance between them. You could increase or decrease the distance between it. It makes no difference on the overall effect or overall electric field. So if you think about how that makes sense, because if you have this same force the whole time, picture this force, this positive. Why do they have the arrow going that way in that? That's ridiculous. Just noticing that picture's got a weird thing going on here. This positive charge, of course, would be attracted to that negative plate. So that is the wrong direction. Electric field this way. I finally noticed that one. Anyways, so the come on, my computer's dying here. So if you were to move these things further apart, think of the energy this thing's going to get as it repels from here and attracts to there. It's going to pick up speed that whole time, right? Well, when you if you want to make these things be farther apart, you actually have to do work on that system. You have to force it apart, right? And so it ends up with a longer. It makes sense that you have more velocity when it gets to the other end because they're further apart because you've done more work on it. If that makes sense, okay? So it's that same field strength the whole time, and of course it has to be because then that same field strength for a longer distance gives you that more speed that you'd expect because they're going from an area of sort of higher energy to lower energy, right? Greater difference there. So some summary points, we've done all this stuff. So all these things, right? All these things, you've seen all of those, right? And then charge parallel plates again means no battery. Last bit for us here is about the electric field strength. Okay, so electric field strength. If we think about gravity, the electric field strength is really the G, the 9.8. G is really force per mass. We never talk about it that way, but it's force per mass. It's how many newtons per kilogram there is on objects. If we talked about it as how many newtons per kilogram there is more often in gravity, this concept we're going to see next for electric field strength would be more obvious to us. We don't really talk about it with gravity a whole lot because we're usually just talking about Earth, right? So we just do G, yeah, it's 9.8, right? But that's certainly telling you like how much force is going to be on you, right? And that same thing is more focused on in electromagnetism with electric force. Okay, so this, instead of G, it's this curly E for some reason with a vector arrow over it. So that's your field strength, just like G. Right? So it's your electric force per charge. Whereas, of course, this was gravitational force per mass. Right? So electric field strength in newtons per coulomb, force per charge. This is your electric force and your charge amount, right? So remember, Coulomb's law, we know, is KQQ over R squared, right? And so what you're going to have is one of those Q's is going to cancel out, right? So you'd end up with KQ over R squared. So you get your KQQ over R squared, and picture Q as being like the charge that you're testing. Q2 is your test charge, right? So your test charge is canceling out. It's not having an effect overall on the field strength. And yeah, so this is the electric field strength around a charge Q, right? Yeah, so curly E, force per charge. And again, we could do the exact same thing with gravity, right? We could say GMM over R squared. And if you picture M1 being the mass of the Earth, then your mass, how much force is on you wherever you are relative to Earth, is force per your mass, right? So they would cancel out, and so you'd have your gravitational field strength is Gm over R squared, the M being the mass of the Earth, right? So that's the gravitational field intensity. This is the electric field intensity, right? So it's a very, very similar concept if you think of it that way. Gravity obviously applies on masses, electrical forces and charges, attraction between masses, and this one is attraction and repulsion between charges. Field is tested by, if you put a mass somewhere, you see how much gravity force there is, or if you put a charge somewhere, how much electric force there is. Meaning of field lines, it's the way a mass would go. A mass would, they say fall here, but it's the way a mass would accelerate. And then the positive test charge would be there to show you which way things would go from the charge, right? So field strength vectors, the G and the curly E business, the units, force per mass, force per charge, this is all review. F equals mg, whereas here Fe was going to equal QE, right? That curly E. So mass times gravitational field intensity versus, and in this case, charge times electric field intensity. So yeah, there's your symbols and your stuff. All right, so just a little bit of calculation work to do with that, and then we're done. So, calculate the electric field intensity at a distance from a charge. You're just going to plug the numbers in, right? So you're going to say, okay, this is this many newtons per coulomb. It's a vector, and so you'd look at it and you'd analyze this situation and say, oh, it's to the right. Okay, piece of cake, really. The only challenge comes up is when you have more than one, right? You'll notice that it says point charge. Point charge is just the idea that it's like, it's fairly small. It's so you can picture all that charge in one spot. So you don't have to worry about the dimensions, if you will, and the distribution of that charge. Okay. So in this situation, you have two charges. And so, it says, one is the positive charge to the left of the negative charge, press pause and look through it and so on. They're 10 centimeters apart and all this stuff, right? Or 10 centimeters away for the one and 50 centimeters they're apart. Like this is the geometry that they describe there. So they want to know what the electric field intensity is at a particular spot. So what you're going to do is you're going to look at the electric field intensity, how many newtons per coulomb there is in this spot due to this charge, and how much due to that charge. If you look, this a positive test charge is going to repel to the right from the green one, and it's going to attract to the right from the blue one. And so you're going to have two forces, both to the right. They're going to add up, giving you the total, right? So this is electric field intensity at y due to charge A. And so we're going to use charge A, the 2.5. And then the distance between is the 0.4, because obviously the whole thing's 50. And we're looking at a spot 10 centimeters from the right end of it. And so numbers plug in and you get your, so this is literally the force to the right from the green one. So I could show, force to the right from the green one, visualize this on here, this number here, and then you go and you calculate the force to the right from the other charge, right? So force to the right from the other charge. Again, the distance now is just 10 centimeters, goes in as 0.1 meters, of course, and so on, right? And you have the charge on the right there is the 3.7, the negative, and yeah. So you're going to get this, and then this, we know that means attraction, and so because it's on the right, it means it's going to the right, same as before, right? Same as when we were doing like Fe equals kqq over r squared, except now we're doing curly E, the field intensity, or newtons per coulomb, rather than actual amount of newtons, right? So to get the result, you just have to add them up, and they're both to the right, so it's easy enough. You just add them up, and if they were obviously in different directions, you'd take that into account and combine them vectorially, and so on. Okay, so net electric field at that point is to the right at 1.7 times 10 to the 6 newtons per coulomb. And visualize the connection to other things we've seen before. If we had a charge suspended from a insulated string, and it's another, the charge is at rest when the string makes an angle of 20 degrees to the vertical, and so on. Basically, it just says draw the free body diagram of the situation. So it's a stressful question. You're reading it and you realize like, oh, I just have to draw the diagram. You would need the mass. You would need the field strength. You would need other information to do more with it, to get like tension in the string, for example, or something like that. But the way it is, the question is just, okay, visualize there's gravity down, there's a tension in the string, and there's a field, electric field force, I should say, an electric force to the left due to the electric field. And it says, place an electric field and so on, right? So the electric field is causing that force. I want to show you here the logic of this is that in to do with our equilibrium stuff that we know, the component of the tension force up is balancing gravity. So it's no net force vertically. And then the component of the tension force horizontally is balancing the electric force, right? So there's no net force horizontally. So it's in static equilibrium. So you could picture, doing the same thing as we've done in the previous unit with analyzing forces in a static equilibrium situation, but there's just a new type of force calculation to do with it. So it's not really any harder. It's just a different calculation to do with different values. Okay. So that's just the note about them being the same. So that is electric fields and electric field strength. And as always, if you have any questions, just post in the help thing or email me or whatever you're comfortable with. And so that's all for now. Thanks for watching.